were doing last time. Otherwise, we will. Okay, we have the L2 version of Hardy uncertainty principle. That is, if this is the L2 version of the Hardy uncertainty principle, and we prove it at least in one dimension because the Hormander-Berlin theorem that we proved that was one dimension implied this one. This is equivalent to say that if U sub 0 and E exponential of IT belongs to L2, if A multiplied by B is larger than 1 over pi squared T squared, that implies that F U 0 is 0. Where e to the I dt is the solution of the free Schrodinger equation. And this was because this simple formula that relates the solution at the time t with the solution at the initial data is something like this. Okay, then you can think that the solution of the Schrodinger equation is the Fourier transform at the time t is the Fourier transform of this quantity evaluated at this point multiplied by something that have absolute value 1. Okay. Let's make everything more simple. Let's put t equal to 1. Simplify the matter. Let's put t equal to 1, that is not a restriction, and let's put a equal to b, that we will remove also. Okay, we are going to remove that. Then what we want to prove, then our statement is this: if the initial data multiplied by this quantity and the solution at the time 1 belongs to L2 of Rn, and A is positive, if A is larger than 1 over 4 pi, then U0 is 0. Okay? We will see that this is not a restriction to be removed. This condition will be removed. Okay. Then, as we prove this, everything is equivalent. And remember that the proof of this uses complex variable. Last time, we were trying to give a proof without using complex variable, and that's what we did. What we're going to prove is a formal proof of the following fact. If U0 belongs to L2 and is A positive if A is larger than 1 over the square root of A pi, then U is 0. Then we are off for a square root of 2. Okay? Then we want to prove this formally. Why do we want to prove this formally? Let's finish this proof. And what we want is to justify that we can prove this in a rigorous way. And what we want is to put potential here, and then to go to a nonlinear problem. Okay? But before going there, let's recall that we were very close to finish this proof. Okay, how is the proof of this? Proof of this statement and it's formal because you are manipulating quantities and doing integration by part and all these things, and you're not justifying any of these things. Okay? The formal proof of this is that you define f to be u exponential of minus phi, or the other way around, u is f exponential of phi. Then f satisfy this initial value problem. Then we write this in the equivalent way, that this is dt of f equal to symmetric part of f plus skew-symmetric part of f, and f of x0 equal to, at this point we haven't decided who is this function that it will be in the exponent, okay? Okay, S is symmetric operator. A is skew-symmetric. S is equal to this, and we prove that it's symmetric. A is equal to I Laplacian plus gradient square. Okay. Then our main claim was the following. Claim, if we define H to be the L2 norm, the square of f, we have that is bounded below by this quantity. Better not remember which is. Okay, 1 second. I have to remember what is minus 1/8 r squared mu. And now I have to say who is phi. Choosing phi of xt to be equal to mu x plus rt 1 minus t e1 squared. E1 is the vector 1, 0, 0, 0, 0. If we assume this, we finish the proof. Okay, let's recall how was the argument. Assuming, because we are going to use this argument several times, it will be different if we put a potential here and so forth. Assuming claim 1, finish the proof. How we call it? Okay. Then what if this statement imply that h of t multiplied by exponential of minus r squared t1 minus t over 16 is logarithmically convex. If you take the log of this, you will see that what you are saying is the log of this quantity, second derivative is positive. Why? Because the second derivative of this is minus 2t. You pass that to the other side. Right. Is this clear? This implies this. Okay. There is a minus here because the second derivative of this is negative, and so forth. Therefore, we have that h of t, in particular, we have that h, let's call this capital F to make it simple. Capital F of t is logarithmically convex, means this, that f of t is less or equal to f of 0 multiplied by 1 minus t, f of 1 t, for all t. This is exactly what you are saying, that capital F defined this way is logarithmically convex, means this. In particular, you have that f of 1/2 is less and now let's substitute this. If you put t equal to 0 here and t equal to 1, you don't see it. Then you have that this is f of 1/2 less or equal to h of 0 to the power 1/2 h of 1 to the power 1/2. Who is f of 1/2? Well, if you evaluate this in 1/2, you have 1/2 and 1/2 multiplied by this, you have exponential of minus r squared well, I forgot the mu here. You have to correct me. I forgot the mu. Please correct me when, okay? The mu has to be there. 64 mu h of 1/2 less or equal to h of 0 1/2 h of 1 1/2. Then you can pass this to the other side, and that implies who is h of 1/2? Well, h of 1/2 is what you have here. F is written here. You have chosen phi to be this. Therefore, what you have is this exponential of this is u of x 1/2 a square exponential. This is real. You're going to multiply f by itself. Then there is a 2 that appears here. X, t is 1/2. Then it's R4. E1 squared dx less or equal. This number you can pass to the other side. Exponential of r squared 64 mu, and h0 is this f phi of 0 is this one. This is h0 to the power 1/2. there is the L2 of this, and then the L2 of this. Is this clear that we have? This is H. This number passed to this side. H0 is this one, to the power 1/2, this one. Okay. Okay, let's see if I can finish this here. It will be nice to see if I can finish here. Okay, suppose then you can integrate here. This inequality is true if you integrate in something smaller. Suppose that you integrate in the ball of center 0 and radius epsilon r/4. I mean, this is still true. You are putting less. Then if you do that, what happens with this part? Let's do the computation here. If x is less than epsilon r/4, then x plus r4e1 is more than just r4 minus epsilon r4, that is equal to r4 1 minus epsilon. Then this quantity, what you have here, is larger. The exponent here is larger than exponential 2 mu r, then I have to take a square for 1 minus epsilon, a square. Second? 4 is 16, right? Then I have to take a square. Then this is 16. Thank you. Is that okay? Yes, because this is the L2 norm square, and you are putting 1/2. Thank you. Thank you. Okay, please correct because it's okay. This is the hypothesis. This is the hypothesis. The problem is who is mu, right? Then you pass this to this side, and you finish with this. This line implies that, well, this is integration in the ball of center 0 and radius epsilon r/4. Then you have that the integral over the ball of center 0 radius epsilon r/4 of u in 1/2 squared dx is less or equal, pass this to this side. You have exponential of r squared, common factor 64, common factor mu squared, common factor that you have mu here. And what do you have in the other side? You have 8. Let's see, I want to be sure that I have it correct. Well, let me put like this. 1. This is A mu squared 1 minus epsilon squared. Right? Because if you divide this, give you 8. The mu gives you the only mu that you have there, the epsilon squared, right? Therefore, and this is something that is finite. Let's call this alpha and beta. You're assuming that your problem is, this is going to be your hypothesis. It's going to be AP. Your mu is going to be A pi. The question is, what happens if this quantity is negative? If this quantity is negative, you have all the right. This is independent of the R. This is independent of the R. You have all the right to take R to go to infinity. This is going to give you 0. This is going to give you the L2 norm of this. And you get 0. Therefore, if 1 minus 8 mu squared by 1 minus epsilon squared is negative, you are done. That is sufficient to say that 1 mu squared is negative, right? Because epsilon is as small as you please. Then what you need is that mu is less than 1 over the square root of A. Right? Greater than. Better. And this is what we have proof here. You decide to call, instead to call this mu, and then you have the proof. Okay, then we prove the theorem. We miss the square root of 2, because the chart theorem gives you 1/4, and we don't have 1/4. We have something a little bit bigger. Okay? Then we have to prove first few things. We have to prove this. Okay? Yes. Then you have that F, that you have that initial data is 0 somewhere. I mean, you have that the solution is 0 somewhere. Then you can, the only way, by uniqueness, it has to be 0 everywhere. Is this okay? Okay, then let's try to prove this part. Then everything reduced to proof claim 1. And this is a general proof. It's a general argument that we are going to use several times. Okay? Then up to now, nothing is new. Then everything to reduce to prove this. And then to try to justify why all this manipulation can be done and how can you insert a potential there and what can you say to the nonlinear problem. Okay, but let's go by step. Okay, then everything to reduce to proof claim 1. Okay. Proof of claim 1. And we were very close to proof claim 1 too, because we have this manipulation that we did the last time, is who is the derivative with respect to t of h? Is dt of f plus f dt of f. And now you have the identity that dt of f is this quantity plus this quantity. If you put this quantity, you get 0. Remember that a of f multiplied by f, since this is skew symmetric, is equal to this. Okay? This is equal to minus this. I mean, if you apply a skew symmetric operator, is 0. Okay? You can do the computation. Not. This is 0. Then we can pass here to write the explicit formula. Instead of put this, you put s of f plus a of f, but this is 0, then this is s of f plus f, s of f. But this is symmetric. You can put that this is 2 times real s of f. And this is real. You don't have to put the 2 there. You can check that this is real. Okay? And just call this is 2n of t, definition. D of t, I'm sorry. Accordingly to some notation that I want to follow. Okay, then who is the second derivative of the log? Is The first derivative of the log is h prime over h. The second derivative of this is going to be h. This is h prime is 2d over h prime. This is 2d h prime minus 2d h squared d prime. H prime. That is correct, right? That's the formula of. This is the derivatives of the first multiplied by the derivatives of the second. But who is h prime? Is 2d. Then this is 2d prime over h minus 2d, 4 dh squared. Okay, this is, up to now, all this is abstract. We haven't done anything that has to do with our particular problem. Right? Therefore, who is the derivative? Who is d prime? This is the derivative with respect to t of s of f multiplied by f. And what is this? This is when the derivative hit here, you have the derivatives of the operator, then f plus s dt of f plus s f dt of f. This is equal dt of f. Then you can pass, if you wish, this to this side. This is symmetric, and then you have twice the real part of dt of f, s of f. You use that f is symmetric, and so forth. Okay. And now you use this trick. Who is dt of f? I have to put the real part. Then you write the dt of f is s of f plus a of f, s of f. Okay, let's write everything. This is twice. When this multiplied by this is real, you don't have to put real part. Plus twice the real part of af this. What is the real part of SA multiplied by this? Then you have here the real part twice the real part of A f s of f. The real part of this number is this plus its conjugate, right? Is that okay? Then, but this one, this is symmetric. I can pass this to this side. This is skew symmetric. I can pass this to this side. Then this is exactly the commutator. Let me write that. SA minus AS FF. And this is the commutator. And I have here, this is plus SA of FF. Okay. Therefore, what is exactly that we want to prove? We want to prove that this quantity is bounded below by this. This is what we want to prove. This operator, as operator, is bounded by the identity multiplied by this. This is what we want to prove. Okay, D prime is this. Therefore, let's write everything now. Then who is d prime divided by h Can I erase that part here? Okay, then this is d prime over h is this divided by h, this divided by h, this divided by h. This part by itself is larger than this one. I claim that this part by itself is larger than this. If I have to multiply by 2d here. 2, 2, 4, 2. I claim that this part is larger than this. This is a positive operator. This is a piece of it. What is this? This is 4. D is SF, F. This is D. H is FF. All this is a square. This is H is FF. This quantity is larger than this quantity is Cauchy-Schwarz inequality. Therefore, this quantity is positive. That means with this part, you kill this part. And then the only thing that you have to prove is that this quantity plus this quantity is larger than that. Then everything reduced to this. Everything reduced to this problem. Let's see if we agree that twice dt of s plus the commutator between s and a applied to f multiplied by f divided by h is larger than minus 1 over 8 r squared mu. Then everything reduced to here. Is this clear? Because I have this piece have 3 pieces. This. This piece alone kill this part because it's larger. Then what you have to prove is that this quantity and this quantity together are bounded below by this expression. Then we have to prove only this. And that is the last thing that we did last time. Okay, then let's prove that. And now, up to now, we haven't used anything that have to do with our problem. We haven't used anything that has to do with this. And this can be stated as an abstract theorem. Whenever you have an operator that you can state that in an abstract way. Whenever you have an equation that satisfies this, right? You have this give you logarithmic convex of some expression. Then we just have to prove this. Let's prove that. And now for that, we really need to go to this definition. Any question before I erase everything? Okay. I claim too that ST plus the commutator of this is larger. Let me write that. Where do I have this? This is equal to this quantity. 4 times minus 4 times the gradient phi, and I will explain the notation. 4 times the gradient of phi, minus by Laplacian of phi minus 2I gradient of dt of phi, gradient of phi, minus I Laplacian of dt of phi. Okay, let's prove that. Okay. This second of this is the matrix of the second derivatives. Okay. Then this is a vector matrix, a vector. Okay. This is like this. Then everything is clear, right? All these are operators. Okay, let's go to, okay. Let's first assume this and finish the proof, and then we prove that. Assuming claim 2, let's prove this statement. Assuming claim 2, let's finish the proof. Proof this inequality. Okay? Then we have still to prove claim 2, but let's see. Okay, then who is 2st of S plus the commutator of this F. It's going to be the first. This is divided by H, okay? This is 2 multiplied by, okay, let's forget for the moment the denominator. I mean, let's work with the top only. And let's forget the 2 for the moment, but we have to return to that. Okay, who is this operator? When you apply this to F, you integrate by part, you apply this, and this part pass to the other side, you have exactly, this is 4, right? Let's see how I wrote that. This is 4, the gradient of second derivatives of phi that is real, the gradient of F squared. Is this okay? You multiply by F here, by F conjugate, you integrate by part, you have this. Plus this one is 4, second derivatives of this, F squared, this one. Okay? Well, this one doesn't appear because this is 4-order derivatives, and this is a polynomial of order 2. Okay? That one doesn't appear. We don't have to go into any of that problem. Let's see who is this one. This is minus, and let's write who is this. Okay, now it's much simpler to write. Well, let's write what do we have. This is 2I gradient of phi t gradient of f conjugate minus I Laplacian of dt of phi f conjugate. Okay. And we want to see that this is not too negative, that is bounded below by this quantity. Okay, now we have to substitute who is the matrix of the second derivatives, the absolute value of the gradient, and all these things. Okay, let's go here and do the computation. Then we know that everything has reduced to this. H is that. Okay. Okay, phi is equal to mu x plus r t 1 minus t e1 squared. Then this derivative with respect to 1 means x1 is twice mu x1 plus r t minus 1 minus t. Is that correct? Let's see where do I have all this computation. Okay. The derivative with respect to the other variables are 2 mu x sub j. Therefore, the derivative for j equal to 2n. Then the derivative with respect to this variable is derivatives again give you 2 mu. Therefore, this matrix of the second derivatives, then this matrix, that is the Hessian of that, is just twice the identity. Okay? Okay, let's compute. Okay, what is the derivative with respect to t? The derivative with respect to t of this is going to be equal to what? Then the only thing that disappears is in the first component. This is going to be 2 mu x1 plus rt 1 minus t. And then the derivatives of the inside. Where did I put this? That is r 1 minus 2t. Is this okay? Sorry? This is a matrix. Okay? Thank you. Thank you. That's the right notation. Okay, thank you. And the second two? Okay. Is the gradient of phi, the second derivative of phi, this is a number at the end, okay? Okay, thank you. Okay, what do I need to compute? What is the thing that we are missing? This is 0. Okay, what is the Laplacian of this? Wow, okay. Okay. Let's see, this is. Okay, what is the gradient? We are looking for this one. This is going to be 0. By the way, who is this? Who is going to be this one? Well, the Laplacian of this is 2n mu, because you are going to add this same time. Then the derivative with respect to t of that is 0. Then you don't have to suffer with this one either. Then we can erase that. The problem is this one. This number is positive defined. This is positive defined. And you're trying to prove that something is bounded below. You want these two to control this. This is a typical thing that when you commute to guys, you want to be positive. Okay, then we need Who is the bad guy here? Okay, the gradient of this. Who is the gradient of this one? Then the gradient of this one is, well, this one, I should have compute first the gradient and then derivative with respect to t, or derivative with respect to t, and the gradient. Then this only depends of x1. Is this correct? Then this is exactly 2 mu r1 minus 2t e1. Okay. Let's see if I have all the terms. I have to be sure that I have all the terms. This one, this one, this one, this one. Okay, let me check my notes. I don't want to keep doing if I don't have all the terms. You see, I'm missing some terms. I have. Okay, let me check this formula because now I'm not sure that this formula is correct. I don't want to keep doing the computation if this formula is not correct. Okay, we have all the computation here. And okay, let's check this formula, and we know everything here. Let's check. Let's prove claim 2, and we will return to this. I'm not sure that this is correct. Let's prove claim 2, because now I have my notation is this one. Let's change the strategy and let's prove claim 2. And then we will return with the verified formula of claim 2, and we do it. I don't want to go wrong with the proof. Okay, chain of strategy, let's prove claim 2. Okay? Claim 2. Okay, who was S? Now you have to give me S was equal to this operator, I, 2 gradient of phi gradient plus this. A was equal to this operator, okay, then who is this? Well, the derivative with respect to t here as an operator will hit here and will hit here, and that's it. Then this part is going to give you minus 2i. This is as an operator plus minus I Laplacian dt of phi. And now we have to do the commutator. And now let's write the commutator. Since we are going to put the commutator and we have a minus I here and I here, we can forget all the I because this is plus 1. This is the commutator of 2 gradient phi gradient plus Laplacian of phi commute with Laplacian okay? And remember that we are working with operator. Is this okay? Okay. Now let's see, we have how many, let's do this careful. We have to do this one. Then we have to do 2 commute with the Laplacian this commute with this, the commutator of this and this. And then we have to do the commutator of this with this. And of course, these two commute because it's a multiplication. And from real, this is real and this is real. Okay, we have to do the three pieces together. Okay, let's do this piece first. What is exactly that we are doing? We're computing. Let's do it here to write it in the simple way. We're going to compute the Laplacian, and we're going to commute with this. That means that we are computing this second derivatives of phi, second derivatives of f conjugate, minus, when you put it in the other way around, second derivatives in k of second derivatives f conjugate. This okay? The commutator of these two is okay. There is much faster way to do it, but we want to do. Okay, of course. No, you have to correct me because I'm doing this wrong. This is Laplacian of this. Now it's correct. Okay, this is. You're going to apply this to f and multiply by f conjugate. Remember, this is what you are doing, f all the time, okay? Is this clear? Is this okay? Okay, what happened is when all the derivative hit here, you have it. Then the only thing that survives is when all the derivative hit here, and then when you have the mixed one. This okay? Twice, one here, one there. Okay. This is what we have. What do you have here? This is twice dj of phi, dj of dk second of f conjugate. This is a very inefficient way to do it, but I apologize. This is k squared. Then we have dj of phi, dj of f conjugate. And this is correct, right? We have this. And this is the other way around. Okay, when you pass the Laplacian here, what do you have? If everything hit here, that's what you have. Then you have minus twice. When you split this, you have dj, dk of phi, dk, dj of f minus, and when all hit the third derivatives. dj, dk second of phi, dj of f. Okay, and this one. You're going to say that you're going to have common term and everything. Okay, what is exactly? Then we have this one. Then this is twice. Then this is dj, phi dj of dk of phi, dk of phi. Summation convention, f. F minus dk of E square. Then you have dj of E, dj of F. Okay. Then when this one hit here is what you have in the other side, then the only thing that remains is when this one hit one of this one. Then you're going to have that this is 4 dj of E, dj dk of E, dk of phi f f. Okay. Then we have all the terms. Is the computation okay? I mean, we have to avoid to do this commutator and all these things if we have all this wrong, because I mean this is going to be. Then I switch the order. Okay, this is clear that this is the matrix applied to this vector. This is a quadratic form, therefore this is exactly equal to 4 times in the mid, right? This is exactly 4 times this gradient of phi, the matrix of the second derivatives multiplied by the gradient of phi, right? This number multiplied by f squared, like this. Then this is a term that appears here. Okay. Okay. Let's go. Now we have only to care about this 4 term that we have here. But this one, let's see, some of them should be equal. Let's see. Okay, which one we have? This one is certainly the bilaplacian. This one is minus the double Laplacian of phi f squared f. Therefore, this is 2. And this is equal to this one. Okay. Now let's see. We have to have this one 3 and this one is 4, right? And this is what we have already here, 3 and 4. Okay, let's see if we have, then we have all these 3 terms to see if our computation was correct. Then this one, we have to do something about this. We have to integrate by part this one. Right? Then let's see. We have these 3 terms that we haven't classified yet. Let's be careful how we are going to write. This one, by the way, this 2 is affecting this also. These 2 go with all 2. Okay. Then what do we have here? Okay. Then this term is, let's see. This is dk. This is dk, dj. I pass this to this side. Okay. Okay. Let me do integration by part in this term. If I do integration by part, in some moment the j will hit here, and that will disappear with this one. And it will be when this appears here. And then I have to do this one. Okay. Okay, I have this. Okay, we have these 3 terms, and we have to figure out what to do. Okay, that's 3. dj. Give me 1 second. This is the derivatives. Okay. This, I'm calling this. The derivatives, okay, what is that term? Is with the derivative with respect to j of dk, dj of phi, dk of f conjugate. Okay. Okay. Let's see if this is correct. If I plug it here, and I plug in integration by part, okay, then I need to be sure that this is the term that I claim that this is the one that I will have here. Okay? Then let's see why I still don't have this one. Then this is the second derivative. Okay, the second derivative, this is. Okay, let's review this one because there is a factor of 2 that is missing. The middle factor here? Yeah. Okay, let's review this part because I think this is a factor. There is a 2 here for the moment. What is the second derivative of that? When you mix one derivative here, one there, that you have this term, there is a 2 here. Right? And when you put all the derivatives in front of this one, you don't have that. But you have these 2 again. Then there is this 4, and there is this 2 here. Okay, I'm sorry, but these second derivatives, when one hit here and one hit there, you have to put a 2. But you have another 2 here. You have that. Okay, now, let's see if we have what we want. This is what we want. Is this equal to this expression? Let's see. Who is this expression? Well, this expression is exactly equal to minus 4 times. Is the derivative hit here? You have dk, dj, second of phi, dj, dk of f. And then when the derivative hit in the other one, this one, minus 4 dk, dj of phi, dk of f. It's not what we have. Let's see. This one is when you have second and second. This is what you have here. And this one is when you have third, 3 here and 1 here, and 3 here and 1 here. This is exactly what you have. Then we are okay. This is this term. Okay? When you put these 3 terms together, you get this one. Then the commutator was okay. Phi is this one. This 3 line is equal to this, because this is equal to phi. Are we okay? This is okay. Now we can continue with our proof with a commutator. Okay. Now, then we have this. Remember that this is what we need to prove. This is our estimate. We already did this part. This part is this one. This part is 0 because the bilaplasian of this was 0. The Laplacian is this. The bilaplasian is 0. Then this one is this one that we have here, and this one is 0. Then we are having 3 terms. Okay. Computation. Okay. Why am I still missing? One second. Give me 1 second. I still want to check that my computations are correct. This is 2i. What did I have? The 2. 2, you have 4, you have 2. Dx1. Okay, then let's write what we have, because do you believe this computation? Yeah? Okay, this one is 0. This one is 0. I don't think that we have any mistake up to now. Then let's write what we have here. What is this? This is 4 times the Laplacian, the second derivative matrix of this is the identity is 8 times mu. Then you have gradient of f squared. What do you have here? This is 4 times. What do you have? This is twice the. You have a mu. You have, this is going to be the gradient of this square. What is the gradient of this? Okay, the gradient of this is dx1 phi d2 phi dn phi. And this is exactly equal to 2 mu multiplied by x1 plus r t1 minus t multiplied by x2, x3, xn, that is equal to 2 mu x plus r t1 minus t equal. Then this is exactly the gradient of this square is going to give you, then we put 2 here, then twice mu x plus r t1 minus t e1 square f square. This is this term. Is that okay? Plus this one. What is the gradient of this? dt. We compute this one here. 2 mu r 1 minus 2t Okay. Then we have to do a lower bound of this. Then let's write this in a simple way. This is 32 cube. You have a square here. You have a square here that is give you a cube. Then you have x square f square plus 64. Okay, mu cube, the product of this with itself, this is going to be, you see, x. This is the square of the, this is x1. This is not the most efficient way to do this, but we'll do it this way. This is f squared plus the double product of the first with the second give you this, and then this. The last one will give you 432 mu cube r square t1 square 1 minus t square f square And this one, we can bound that from below, that, okay, minus 2I, this is 4, mu r 1 minus 2t gradient of f. Okay. Which are the good terms? The good terms are the positive one because you want to bound this from below. This is good. This one is good. This one is not good because it doesn't have a sign. This one is good. And this one is not good. Okay? Okay, then the only way that you can bound this one is if you use this and this. Okay, let's start to do this kind of estimate. We develop this square. Okay, then A1, good. Okay. Then we have A times I R1 minus 2t dx1 of f. Let's see if this is, where did I put this one? Only the first component. Is that correct? Okay, this, where did I put that one? The gradient of this is only in the first component. Then we have this. What is exactly that you say, Anita? The first component? Okay. Thank you. This is derivative with respect to the first component. Okay. And we have, let's see that we have the right numbers. We have 2 here. We have to, I need to be sure that all the numbers are correct. If not, we're not going to get. Then this is 2. This one was derivative with respect to t of this is 4. See? You have this. And if I take derivative with respect to t here, I will give 1 minus 2t. No, it's okay. I have. This is this one. Okay, this is this one. This is the first component. And I have 4 here. Okay, let's copy this. Well, except if we have a mistake with the computation, we have this. We have a 2. By the way, we have a 2 here if you want to put the 2 in the front. There is a 2 that I forgot here. Okay. Then the bad guy is this, and we're going to use this. This is less than 2 mu I'm using mu. Mu. Okay, this is 2 mu r squared 1 minus 2t squared gradient this f squared plus a mu dx1 of f squared. I'm using the following, that 8 is equal to 2 multiplied by 4. Then 8 mu is equal to 2, square root of 32, mu 3/2, 2 square root of 32 mu 1 half. Then let's see. Then I have this is okay, and the second one that I need is okay, this is not so complicated. Let me write this one this is the one that is bad, this is the one that is bad. Let me write the two of them, and we will do the computation here, and we will finish. That's easier to, I don't have to go there. Then the bad guys are this one, 4, that is a mu r 1 minus 2t dx1 of f conjugate. Is that? This one is bad, and this one is bad, and this is multiplied by 2, all this. And 2 by 64. And you have mu s cube x1 plus r t 1 minus t e1. I don't have to put e1 f squared. Okay, these are the bad guys. Okay, then I can take this part out. This is no plus, this is like this. R. You have to 1 minus 2t, this is 4, 8. And mu r 1 minus t, t1 minus t1. T 1 minus t x 1 f squared. Okay, these are the bad ones. This is okay. Okay, then you're just going to use for this one, you're going to use this. Okay, let's compromise the finish of this. What is exactly that you have? You have 2 guys that are bad, and you have 3 guys that are good. And now all the constants are too complicated to carry out because, okay, which are the ones that are good? This one. This one. And there is another one with the x that have to be good. That is 32 mu squared r t 1 minus t. And then this is f squared. Okay. Then you have to use, I have to have an x somewhere that is good. This is an x here. Okay. If you use these 3 quantities, right, and you have a patient, and then you just have to use Cauchy-Schwarz, and there is no technique that is going to give you a problem. What is the trick? This part, for example, the part that have R has to be killed by this. Then you have to carry everything with this. Then I see I don't have a square. Then this part have a square everywhere. Then you're going to use this formula several times in the appropriate way to finish that these 3 positive and these 2 that are not signed, they give you the bound exactly that you need. That if you add here R squared 1/8 mu ff. If you add this, these 4 guys control these 2 guys. Okay, I refuse to do this computation because there are too many constants and I will not control. Then why is this? You can see that this one and this one you have to compromise this to kill this pair that give you some power of x that you can to kill this one, right? And this one have to be killed in this part. And then you have to be sure that everything that remained is in terms of this sense. Because then if you add this here, you kill this part and you prove that. Okay, I'm sorry, but the computation is too large. Okay, then let's see what we have proved and what we want to prove next. Then we prove this if u0 by exponential of a pi x squared and the solution at the time 1, exponential of a pi x squared belongs to L2 and a is positive and a is larger than 1 over the square root of 8 pi, that implies that u0 is 0. This is what we prove. What exactly that we want to prove? Then, remark, we want to justify the step. Justify that you can do what you just say. Formal argument. What do you want next? I don't want to do this. I want to prove this. Remove the condition that A in both sides. You don't have to have the same A here and A here. Okay, this is going to be a trick. 3, that is the key of the matter. We don't want anything to have to do with the Fourier transform. What we want is this. We want to prove this. Where U is solution of this problem. And B, such that B, let's say, is real. B from Rn into 0, 1 is a real potential. That's not necessary. We can prove it if B is L infinity in Rn by 0, 1. And the limit when R goes to infinity of the NOR L1 in times L infinity in Rn minus the ball of center 0 and radius R is 0. That means that you have to have some decay. This potential has some mild decay. You cannot put a constant there. You have to have. Suppose that we can prove this. Then we have the following nonlinear theorem. 3 imply this following nonlinear theorem. Suppose that you have let U1, U2 be okay, and now you're going to complain because I haven't defined solid spaces, but all of you know that. Okay, suppose that this function have enough regularity. Solutions are solutions of this equation. a solution of this equation where f of 0, 0 is 0. That means that it's nonlinear. F is of class C, K, K larger than N. I'm not trying to be sharp by any means. There's some nonlinearity. And F real. If these two solutions, you evaluate these two solutions at the time 1, at the time 0, and at the time 1, are in L2, with this A larger than 1 over the square root of A pi, then U1 is equal to U2. What you are saying is, if you have two solutions of this nonlinear Schrodinger equation, if you dislike this, put your alpha minus 1 here and put that alpha is sufficiently large or smooth to make a smoothness, okay? If these two solutions satisfy that they are very close at time 0 and at time 1, they have to be exactly the same. By no means you are assuming that the solution agree anywhere, okay? This is a kind of new theorem in that regard. The proof of this is completely trivial if you know this one. Because you take the difference, and if you are in this Sobolet space, right, you satisfy this kind of result. Therefore, to prove this is a big deal because you can say something nonlinear. Therefore, this is the theorem that we would like to prove. Of course, it's much more complicated than what we try. Then we will, as you see, there is a huge manipulation of constant that I clear that I cannot manipulate even one constant. I have problem with. Then with 3 constants, I will be unable. Then we have to believe that some step can be performed if you have the patience. Okay, then let's start. To get here, we can do these 2 steps today. At least we can justify how can you remove the condition that you have the decay exactly the same. You want to put A and B and have the condition in A and B. And let's see why the formal argument is so complicated. Okay? Let's start why the formal argument is so complicated before doing that. And we will start Let's start with something completely different. And this is Kato 83. Why with the KdV things are so simple? Suppose that you have a solution of the KdV that is this one. It's equal to 0. Linear. Let's suppose linear. This word for the nonlinear, but let's assume. Suppose that you have that U0 by x exponential beta x is in L2. Suppose this is in L2. Suppose that you decay to the right, beta positive. What can you say? Well, suppose then you say, well, let's formal. And formally you have the following. Define u of xt exponential of b of x, b of xt. Therefore, u of xt is equal to exponential of minus bx, b of xt. Then what is the equation that this satisfies? Then you have that dx here, it becomes dx minus b Therefore, the equation that you satisfy for the B is this one. B satisfies this equation. Because one derivative in X for the U is to apply this operator in the B. Formally. But who is this? This is dt of B plus third derivative minus 3 times B second derivative plus 3 times B squared first derivative plus B cubed B. And now, can you solve this? This is constant coefficient. Well, this gives you a group. In the side of the Fourier transform, this is this plus or minus sign. This is the heat equation. If beta is positive, this is the heat equation. Then this is 3. You have minus 3 beta, and here you have minus c squared. This is a translation in the side of the Fourier transform. This is exactly multiplication by I, C, and this is something that grows with T. Then you are solving, this is dt of B, something that is a group. This is a semigroup that is the heat equation. This is parabolic. This is a translation. And this is just multiplication by an exponent in T. You can remove this by multiplying by exponent of T. This is a translation. This is what you want to solve originally. Then you have this. This is the heat equation. Then you immediately get that if this is in L2, if B sub 0 of X is in L2, you get that your solution is infinity automatically for T positive. Therefore, you get that B is infinity for T positive. Therefore, you can prove that U is infinity for T positive. Right? You can. This is Kato idea. You have, therefore, this is the picture. If you decay in this direction exponentially, you are parabolic in this direction. Therefore, in the moment that you are parabolic, you have convolution with the Gauss kernel, you get all the regularity that you have. Is this argument clear? Suppose that you try to do the same argument for the Schrödinger equation. Let's go in one dimension. Okay? Repeat the argument for the Schrödinger equation. I mean, everything that is, since goes that whenever it is true for the KdV, it has to have an equivalent relation in the Schrödinger equation. Let's put n equal to 1, Schrödinger free. And you repeat the argument. You say dt of u is equal to I dx second of u. And I'm not considering Gaussian yet. I'm considering something that is linear exponential, okay? And suppose that u of x0 is equal to u0 of x. And suppose this is in L2. And you want to say, what can you say if the exponent to one side is this, for beta positive. Okay? Then you were going to repeat the argument. B is equal u of xt exponential of bx is equal to bxt. Then you have that the derivatives in x are exactly what they were before. Right? Therefore, this, for the B, satisfies this equation. This is B0. Okay, in the side of the Fourier transform, who is this? Suppose that you take Fourier transform and want to solve this problem. Then you have that B of xt is the Fourier transform of all this. When you take Fourier transform of all this, what do you have? In the Fourier transform, this is going to be I. This one is minus c squared. Forget the 2 pi and so forth. What is the derivatives? This is minus 2i cb plus b squared. When I take Fourier transform, is this. Therefore, the solution, explicit solution of this problem is this one. It's exponential of minus I c squared. This is going to give you plus 2. Then the derivatives is, well, let's suppose that we put it, the derivatives is give you I c. Then it's going to give you plus I c. This I with this I give you another minus. It give you plus is this. This give you plus I beta squared. All this multiplied by t b0 like this. Question, is that in L2? You start with something that is in L2. Here you start with something that was in L2, and you are taking this one that is a group, this one is a translation, this is a multiplication in T, this is a convolution with the Gauss kernel. Then you put together, you have it in L2. Let's see what happened here. This is complex. This part gives you a group. Right? This is complex. This is not going to change the L2. What happened with this? Do you stay in L2? If B0 is in L2, do you stay in L2? No, because this may grow. See, suppose that you're taking that B is positive. Then if C is positive, then you are growing. Then you cannot claim that this will be in L2. Then you don't apply this argument. This is not in L2 necessarily. Doesn't imply that this is in L2. Then what is the problem? But suppose that you insist, you say, no, they have something to do, this problem has to have an equivalent here. What is equivalent? I mean, you have to insist because everything that is true for the KdV in some way has to have an equivalent in the Schrödinger equation. At least morally, that should be true, right? Then what do you say? Well, suppose you're going to say this. If you give me this, this is my solution. Well, you say that if I start here, this is time, and this is the space. When I have negative frequency, I am parabolic with T positive. And when I have positive frequency, I have to force this to be negative. I solve it backward. Right? Then what you have is that the positive frequency are okay when you are backwards, and the negative frequency are okay if you are forward. Okay, and what is our problem? Now let's go back to our problem. Our problem is that we fix something that decay in this time and this time. Then you have something that decay here and something that decay here. Right? And you want to have decay in the middle. Suppose that you know that the solution exists. Suppose that you know that the solution exists is 0t in L2. Let's put one dimension. Suppose that you know that this part is okay at the time 0, and this is okay at the time 1. This is the kind of thing that we are doing. We have at 2 times. We never say that we know how to prove things in 1 time. That's not true. Right? Then what do? Well, you're going to say, I'm going to do the following. I'm going to prescribe the positive frequency here, and I solve this backward, and I prescribe the negative frequency here and solve this forward. And I put it together, and I will be able to do the thing. This is going to be the idea. Okay? Then what is the theorem that we want to prove? The theorem that we want to prove is this. Then, by the way, everything starts to have a problem with exponential. If you are in the Schwartz class, if your initial data is in the Schwartz class, the solution is in the Schwartz class, nothing happened wrong in the Schwartz class. The exponential starts to bother you. Schwartz class is not a problem. Exponential decay is the problem. Then we're going to be able to prove the following estimate. Lemma. Suppose that you have U continuous in 0, 1 in L2 of R, solution of this problem. With B then there exists an epsilon such that solution of this problem and B in L infinity in Rn by 0, 1 is less than epsilon, and B belongs to L1 in 0t, L2, suppose then if your initial data, exponential of B of x1, and your solution at the time this is in L2, is this, then the supremum is less than some constant plus H E L1 in 0t, L2 in R, and this with C independent of beta. This is the first justification of this kind of exponential decay. Okay. What is exactly that you are saying? Well, suppose that you don't have potential, that you are in this situation, that everything is constant coefficient, you don't have external force. Then you say, okay, you give me the solution here, you give me the solution here. I project here, you give me the solution at the time 0, and you give me the solution at the time 1. I mean, that is given. It's not that you give me these 2 and I can find the solution. No, that's too overdeterminate. You give me this, I take the negative projection, and I solve this forward. This is a parabolic problem. You give me this, I project this, and I solve this backward. These two, this one and this one are move completely independent because you have constant coefficient. Then you give me what I know at any time here, who is the projection of the positive part and who is the projection of the negative part of the solution. All this argument is dead in the moment that you put something that mixes the projection. And who makes the projection? This potential. When you project here, you project into the frequencies. Suppose that you're in one dimension. You have no right to say the projection of this, the projection of that. Right? Therefore, you cannot do this trivial argument that has this. Then what is then there is two statements here. What is the trick that we are going to use? The main trick will be the Calderon commutator theorem. And how do you pass from... in no moment you are concerned with linear exponential. We are concerned with Gaussian. But if you have this, it's a trick to pass to Gaussian. Okay? Then the next time we are trying to prove this estimate. Of course, you can see that I'm not quite good to carry details with constant on all this. As you can see that I get mixed up. Then I will show you the key argument in this instead of going to the proof that is too long. Okay? We will get what is the estimate. Okay? The first thing that you cannot do, the first thing that you would like to put is to put exponential here, and compute things. You cannot do that because you only know this and this. You only have that this quantity and this quantity are final in L2 at the beginning and at the end, but you have to prove it in the middle. Then you have to truncate things, right? And take limit. And we have to see how you truncate and take limit that you can pass to the limit without making any problem. And the big thing here is everything has to be independent of the beta. Okay? Then we will prove that next time. And you will see that this is the beginning of the justification of one step. We pass to the quadratic. We know, and we will explain how you can remove that these beta are different at two times. Okay? We will do that next time.